Welcome back to your fourth distance learning lesson. Today we're going to be looking at the work done on a gas as well as kinetic theory and derivation of pressure on a gas. Let's get started as normal with your knowledge retrieval. Pause the screen now and take 3 minutes to complete the 4 questions. Right, let's go through the answers then. Question 1 asks you, what is the relative molecular mass of a substance? Relative molecular mass is the sum of all the relative atomic masses of each atom that makes up a molecule. So for example, if we have carbon dioxide, we know that we've got CO2, 1 carbon and 2 oxygens. The relative atomic mass of carbon is 12 and the relative atomic mass of oxygen is 16. So the relative molecular mass of CO2 is 12 plus 16 plus 16, which gives us 44. Question 2 asks, what is the Avogadro's constant? Avogadro constant is the number of atoms in 1 mole of any substance. It's specific to carbon-12 because that was the first thing that was tested on in terms of Avogadro looking at this constant. Numerically, it was found to be 6.02 times 10 to the 23 per mole. That's how many atoms are present in 1 mole of a substance. Question 3 asks you to write down the ideal gas equation for n moles, state which each term in the equation represents. Ideal gas equation in terms of moles is given by PV equals nRT, where P is the pressure measured in pascals, V is the volume measured in meters cubed, N is the number of moles, R is the molar gas constant, which is a numerical value of 8.31 joules per mole per Kelvin, and T is the temperature given in Kelvin. And question 4 asks you, what is the Boltzmann's constant? Boltzmann constant is the gas constant for 1 molecule of gas. Essentially, it is the R divided by the Avogadro number and has a value of 1.38 times 10 to the 23 joules per Kelvin. Okay, last time then we were looking at our ideal gas equation. One little further thing to think about in terms of the ideal gas equation is the work done on that gas. You know that if a gas expands or contracts at a constant pressure, work must be done on that gas. There is a transfer of energy that takes place. That transfer of energy normally involves heat. Okay, so if we think about it, if we have something like a balloon full of gas and that balloon gets heated, then the gas inside the balloon is going to expand and we expect to see a larger volume occupied by that gas. Likewise, if we remove that heat source, so this arrow here is representing heat, if we remove that heat source, then what we'll expect to see is that that balloon will contract either back to its original size, or if you make it colder, it's going to shrink because the heat is transferred back into the surroundings. The work done in changing the volume of a gas at a constant pressure is given by the following equation. Okay, so work done is equal to the pressure multiplied by the change in volume. And again, this is measured in pascals, and that's the change in volume measured in meters cubed. We could also see this from one of our pressure volume graphs. So for example, if we have pressure plotted against volume, and we have a graph that looks something like this, then the area underneath that graph represents the work done or the energy transferred to change the volume of gas. So we could have That's our original volume. That's our new volume. That's our change in volume. And that's the pressure. Then all of this area here represents the work done. Let's have a look at an example then. Example says that a gas cylinder is heated so the volume increases from 0.32 meters cubed to 0.875 meters cubed. Assuming the pressure remains constant at 1.15 times 10 to the 5 pascals, calculate the energy transferred to the gas. So we know energy transferred is equal to the work done. And we know that work done is equal to our pressure multiplied by our change in volume. So we want to first figure out the change in volume, which is 0.875 minus 0.320. Which is 0.555. And then we're going to plug that into our equation, which is 1.15 times 10 to the 5 multiplied by 0.555, which gives us an answer of 63,825 joules, which is the same as 63,800 joules given to 3 significant figures. For your exam, you may be asked to derive the pressure of an ideal gas. This is a tricky and non-trivial part of the course, so make sure that you're paying close attention to this bit. It's going to go quite quickly and it's going to take us a fair few steps, and we'll also need to make a lot of assumptions that you also need to know about. Make sure that you pay attention and remember to ask any questions if you do find yourself becoming confused at any part. So, we're going to start by deriving the pressure on one wall of a box, and we're going to look primarily at first in the x direction. So we need to imagine a cubic box. We're going to think about this box and we're going to say that this side has length Lx. This is length Ly, and this is length Lz. We are going to say that we have one molecule inside of this box, although in reality we know that there are millions and millions of molecules inside this box. I'm going to call this molecule Q. It has a mass m, and it's going to travel with a speed of u. And we're going to say that this has a speed of u1. If we were thinking about another particle that was travelling in the same direction, we could say that that has a speed of u2 and u3, etc., etc. Now, at some point later on, we're also going to be thinking about particles that travel in this direction. And we'll say that they have a speed of w1. And we could also think of particles that are moving up or down in the y direction. That's going to have a speed of v1. But for now, we're just going to focus on this particle here. So we know that if we want pressure, we are looking at the equation pressure is equal to force over area. But how are we going to find the force? Well, from our mechanics topic, we should remember that the force is equal to the rate of change in momentum, which is normally given to you by F equals delta mv over t. Now, because we're talking about our one particle here, I'm just going to substitute in u for v instead. So that is our change in momentum. In reality, if we think about what happens when our particle strikes the wall, and we're going to call the wall A here, if that particle strikes wall A, it's going to rebound with the same momentum that it initially strikes the wall with. Now, momentum was, remember, mass multiplied by velocity. So it's going to rebound, or we're going to get a change in momentum of minus 2 mu over t, because it's struck the wall and then gone off in the other direction, so hence the minus sign, and we have mu minus minus mu, so total minus 2 mu over t. Now, we also need to figure out the time that it takes for our particle to do that. Essentially, this t is the time it takes for a particle to travel from one side of the box, over here, to the other side of the box, and then back again. So it's a there and back again job. We know as well that time is equal to the distance divided by the speed. So our time is going to be 2 multiplied by Lx, because that's the distance it travels, one side of the box and back, divided by its speed, u. So we can now substitute this equation here in for our little t here. So force is going to be minus 2 mu over 2Lx over u. These things will cancel out, and we're going to end up taking the u up to the top. Therefore, force is going to be equal to minus mu squared over L. So there's our force. Now we need to think about the area. And again, we're just going to think about one face of the box so far. So one face of the box would be the same as doing our area is equal to Lx multiplied by Ly multiplied by Lz. If we are multiplying the three sides of a cube together, you know that that is the same as having the volume of the cube. Therefore, our pressure is equal to minus mu squared over L, sorry, not L, V. So there's our pressure. Now, that's for one particle. For lots and lots of particles flying around, okay, we don't really need to worry so much about the minus sign, because they could be randomly hitting and striking back surfaces at any point. So in reality, while it matters for one particle, for many particles, we can say our pressure is just mu squared over V. Okay, so we've got our pressure that's acting on one face of our box. But now we want to start thinking about the whole box. So if we think about the total pressure, we'll end up with m over v multiplied by our particle u1 squared plus another particle acting in the same direction, u2 squared plus u3 squared plus so on and so on. Now we can generalize that there as n molecules, which means that we can put that back into our equation for pressure, and we'll end up with n times by m over v multiplied by the average speed or average velocity of our particles squared. So that little hat above the u there just means average. Now, that's for particles that are all moving in the Lx direction, i.e. ones that we've given for a speed u. We also want to think about particles moving in Ly and Lz directions. So we need to look at the velocities u, v, and w. Now, I don't want to have to deal with all of those three-dimensionally, so I'm just going to call all particles acting in all directions like that C. If we are looking at u squared, okay, so the u mean square speed, then you can see that actually we're only thinking about 1/3 of c at any point. Okay, so our mean square speed in the u direction, or looking in the Lx direction, is going to be equal to 1/3 of c. Now, it's not just c, because if we're looking at u, v, and w, we're looking at an average speed in all directions. And because we're already looking at the average speed in the u direction, we have to then define something which is called the average of an average, which we call CRMS, or the root mean square speed. That's going to become important. You've probably already met that in certain parts of electricity, like the RMS voltage, but now we're looking at the RMS speed. So we can see that the mean u squared is equal to 1/3 of c squared RMS. If we substitute that back into our above equation, we end up with P is equal to 1/3 NmCRMS squared over V. We want to rewrite that so it looks a little bit similar to our ideal gas equation. So therefore, we'll just slightly quickly rearrange, get rid of the V underneath. We end up with PV is equal to 1/3 NmCRMS squared. And that is our derived pressure equation. So P is measured in pascals, V is the volume, it's measured in meters cubed, N is the number of molecules in the gas, M is the mass of our gas molecules, it's measured in kilograms, and C is the root mean squared speed. And it's measured in meters squared per second squared. Okay, so now that we've got our derived pressure equation, then we will be able to figure out some assumptions that we've had to make to arrive at this equation. They are just as important for you to know as the derivation, because more often than not, you have to describe or state 4 or 5 in exam questions. Now, most of the time in your A-level exam, this second part of the equation, so the generalized equation for the entire box, this part, you don't have to derive. The stuff that you will have to derive is the thing that we saw on the previous slide, so this stuff here, leading us to that equation that I've circled at the top of the page. Let's take a look at the assumptions that you want to make now then. Okay, so in order to derive our kinetic theory equation, we've obviously had to make a fair few assumptions. Now that's because we are dealing with ideal or perfect gases. Now, a few of you have asked some questions before this lesson on ideal gases, and we've said that actually they are quite good approximations for how real gases behave. But obviously we are making some assumptions when we're talking about the other gas laws that we've met too. So perfect gases, ideal gases, actually aren't perfect. They don't follow Boyle's law perfectly. And that's because Boyle's law assumes that particles don't have any of their own size or volume themselves. It's the same thing in this equation and during this derivation. Particles have negligible volume. And that's not the only assumption that we're making. There are actually 5 key assumptions in total. And it helps if we can remember the 5 key assumptions by looking at the following mnemonic device. Okay, so there is the 5 main assumptions that we're going to assume. So V stands for volume. And in fact, there is a negligible volume compared to the volume of the gas for the molecules. Okay, so the molecules of gas have negligible volume especially when compared to the volume of the gas. Next up, we've got R. Now, R stands for random motion. We've just derived that equation for one particle that we said initially moved in the x direction, but of course we have millions and millions of particles moving randomly in all 3 directions. So we have to assume that there is random motion of particles. A stands for attraction, or rather the lack of attraction. In our derivation, we've assumed that the particles aren't attracted to one another, so they won't be brought together by any forces of attraction. So attraction, there are none between the particles. E stands for elastic collisions. Sorry, my writing was really terrible there. Okay, so you know from the law of momentum that all in these types of collisions, all kinetic energy is conserved. So we've got completely elastic collisions occurring within our box. Therefore, kinetic energy is conserved. And then finally, D stands for duration of collisions. Now, for our assumption to work, for our derivation to work, the duration of collisions is actually very, very short compared to the time between the particles moving from one side of the box to the other. So, duration of collisions is very short compared to time between collisions. Okay, so those are the 5 main assumptions that we have made for our gas in order for it to be ideal. Real gases will behave like ideal gases as long as the pressure isn't too big and the temperature is reasonably high compared to their boiling point. So they're very, very useful assumptions. And like I said, most of the questions that are set up in your A-level exams usually start with you having to state at least 3 of these 5 assumptions. So make sure that you know these assumptions off by heart.